All right. First of all, thanks everybody for the invitation. Thanks to the PlanMat team for involving us in involving myself and Francesco Sauro from the PANGAEA team in also participating as in the advisory board. So what we're trying to do is, first of all, I'm Loredana Bessone, and I'm leading the ESA CAVES and PANGAEA training program. So I'm working in ESA at the Astronaut Center on training astronauts. So the introduction that Francesco, who's actually a planetary geologist and a speleologist, and he's much more relevant for you guys to talk about the application of VR in geology. I'm going to give a brief introduction about how VR is used currently and plan to be used in the future for training and also operations in our team, in the ESA team. So first of all, I assume that at least some of you will be familiar with spacewalks and extravehicular activities. This is an image from the AMS EVA, where Luca Parmitano and Dave Morgan have been replacing an instrument that was allowing to continue a very important experiment that was done in collaboration with CERN, and that happened just a year ago, more or less, a little bit more than a year ago. So during this EVA, astronauts have to do exploration activities in space, but they have to do very, very careful activities. So a typical example of how how EVR is used in astronaut training is exactly in extravehicular activity. Before I go further, I want for you to see a video. So this is a briefing. It's actually an outreach briefing that you all can actually find on the internet, and this is used for outreach purposes to explain to people what the EVA is about. But what you can see is actually the sequence of what activities are, and it's accelerated to show everybody what happens, but it's allowing to see what needs to be done. It has a high level of fidelity. It's done with a system called DUG that is maintained up to date with the current configuration of space station, and is used both in training of astronauts, then in planning operations, then also in outreach activities. And it's very, very important that it's maintained up to date, and you can speed up activities because it allows to do a lot of things like real design of operation, real astronaut training, and real briefings for outreach activities. And this is very, very important. It's important to keep all these elements in mind. So preparing for a spacewalk now is obviously involving working with real actual equipment, but that doesn't allow you to represent how that will be moved in microgravity. So there are other tools that are used like suspension tools, where you are allowed to move around and see what it does, trying to use a tool that will turn you around is when you don't really have any way to sustain yourself. But then the next level is obviously to do these things in a real representation of the space station in an analog setting, which is an artificial analog, typically is a pool, which is reproducing some level of zero gravity. Actually, this is all good, but it doesn't allow you to represent the reality of what the space station is. And that reality is represented with virtual reality. Not only, but there is another element of training in virtual reality that you cannot do in real time in any real environment, which is operating something which is which is in the backpack of your EVA suit that allows you to return to the space station in case you're unable to return because you detach yourself. So there are applications of virtual reality that complement all of the other training. So what is important in VR in astronaut training? First of all, readiness. It's important that you do things from simple to complex. So you need to make sure that you start with very simple applications. You start with mock-up, and you do the last training in the more realistic, like analogs. But sometimes VR comes in as even better than analog, because you might not be to actually represent what you're doing in analogs. Efficiency is very important to only train what is necessary. So you need to focus exactly on what is required. And sometimes you need to speed up because you don't want to waste time waiting for a robotic arm to be moved from one place to the other when you're training the specific of an operation, for example. So simulations of VR are very useful for that. Fidelity is very important. And that you need to use the most realistic, and if it's not possible, the virtual environment, to be able to represent what is reality. You don't want to train somebody to make mistakes. You also need to create a consistent memory. So you need to use all possible senses consistently. You've seen highlights in some of the parts to focus the concentration on those elements. And that's very important. So the 3D visual is important. Haptics becomes very important. But in some cases, smell is important. And that maybe is not possible to be represented with virtual reality, although there are new systems that allow you to do that. And typically, virtual reality is using rendezvous and docking, robotics and EVA to create or visualize experiences that cannot be otherwise reproduced, because you can obviously not create a video of how you move around in extravehicular activity or how you move around with a robotic system in the real environment of ISS. So in the future, planetary surface and subsurface exploration can also be supported because we cannot fully represent those systems in analog. So even in actual analogs, field analogs. So the VR projects that of the team at EAC are multiple and go from teaching tools like Jive, from Moore software simulation, architecture design for artificial articles, design assessment for future models in ISS, from teaching in extravehicular activity, for trying to represent different level of gravity. Also in medical anatomy training, allow you to go inside the human body. And then the application that we're using for PANGAEA VR, but also to test suits, different constraints of suit that you can try to replicate constraints at different level of gravity, but also with different suit configuration. And then testing for different tools that would replace totally, because sometimes it will need to be possible when you're going to Mars, to totally train in virtual reality because you haven't been able to train before. And this is an experiment that is currently ongoing in ISS. So our XR lab in EAC is using VR, but also starting using augmented reality to design new tools for astronauts training, for operations, and also to conduct experiment. And it's very important to understand what is the do's and don'ts of VR with respect to a classical training, because there are things that you can do in classical training that are more complex or better with VR, and you need to understand to focus on them. They're also experiment, as I said, on board training on the ISS right now, and also trying to work on experiments to be used on the ESA contribution to the gateway for going beyond LEO beyond the low Earth orbit in orbital type of activities, and also on Artemis for moon exploration. There are three areas that are covered at the moment. One is interaction with technology, where collaboration is very important for remote teaching and design assessment. So robotics and spacewalk are some of those, and sometimes they are combined. Anatomy, I mentioned it, and there is very good tools that are used that our medical team is testing on that. Designing artificial analog, we're working on designing what is called Luna, an artificial analog that will allow to do a lot of testing for future gateway and moon activities, and also for testing experiments like also emergency and representing various gravity level. I was mentioning the exoskeleton. It's important to test different gravity levels when you're working with a tool, and in order also to develop tools that are going to be useful. If you're thinking about designing even a table on the moon, you can jump from one side to the other to the table. But if you don't think about that, when you're designing a habitat, you might actually jump on the floor and hit yourself. So it's important to think about those things too. So this is a typical, this is one of the tools that is being designed right now. This is an exoskeleton. It's testing different tools, different constraints from the suits. So currently designing EVA suits is very important. And this one is testing the current EMU or ISS suit. But you can actually, in the VR system, you can change the constraints of the suit, and testing also the new EMU suit, which is the one currently designed by NASA for EVA, or different ones with different level of gravity. So that's very powerful at the beginning. Obviously, the level of fidelity is not the same as the suit itself, but it allows to go in steps. Other applications are training and outreach, and this is a typical representation of the ISS, interior of ISS, that is used mostly for outreach, but also to do some test of some of usage of VR in haptics. And whoops, obviously I put it in the background, sorry. I think this was not a very smart move, so I think I'll try to bring it to front if I manage. Sorry about that. I hope that works. In this case, you will see that it's very nice, but not always this is useful for training. Sometimes it's useful for initial training, but if you look at the ISS right now, it's not like that. This is how it looks when it's very clean, which is 20 years ago. So now it's full of mess everywhere. So this is most useful for outreach, but this has been built very quickly by a company that works, Pale Blue, a Norwegian company that works in designing collaborative VR tools for doing maintenance in remote stations like oil platforms, for example. And they have been able to develop it very quickly. So this activity, for example, which is tilting a rack and seeing what's behind, is a typical activity that is very, very complex to do in normal environment because they are very, very heavy. And collaborating in doing that can be very useful if you're having a VR tool, but mostly otherwise, this is also very useful for VR purposes. The other application of VR is obviously geological training. So we are coming much more on what is closer to your art. And this is actually something for which you see plan map in there. It's not just VR, where you could put the scientists, pretty much bringing the scientists to the field in together with the astronauts, but then also augmented reality, where the astronauts could actually see through the geology and be able to go beyond what their visors allow them to see also the structure behind in a help to actually become even much better collaborator for scientists. And this type of application is the one that we've been using for, or we're using in our PANGAEA training. And I think the best is that I'm passing on to Francesco Sauro, that is introducing to you PANGAEA and how we're using VR in astronauts training.
Thank you, Loredana. I hope you can hear me. You can go to the following slide. Okay, thank you for the introduction. Yes, we are working now, Science 2016, on PANGAEA. PANGAEA is a training program from the European Space Agency. PANGAEA is a planetary analog geological and astrobiological exercise for astronauts. And why we started a few years ago with this training, because let's say that in the last 20 years, most of the astronaut activities has been related to low Earth orbit, so the International Space Station, near before. So there was not any need really to know about geological environments, but look into the future of space exploration. So the return to the moon, also with Artemis, and the future also to Mars. Geology is becoming really the main focus of this kind of mission. And so astronauts need to be prepared to really achieve the most out of this very delicate and expensive missions in terms of science return. So this can be done through training, but as you probably many of you are geologists or are working in geological environments, knows that this is very difficult if we cannot experience really the environment and experience directly on the field. So the PANGAEA is a training which is taking about 3 weeks. The crew is mostly done by astronauts, but sometimes we had also mission developers. And the instructors are a mixture of planetary geologists, but also experts in different operations, for example, space operations and so on. Because we have to merge the expertise of astronauts together with the one of geologists and of mission planners. You can go ahead, Loredana. Okay, one of the major lessons learned from Apollo missions is this sentence by Schmidt that said, "No substitute exists for working in the field to learn the principle of geologic field observation and sampling." And this is absolutely true. And so, for example, PANGAEA and also other geological training are being focused mainly on field work, not on lectures or too much notional aspects of geology. But in this framework today that we are talking about VR, we can say that probably the most close substitute for work in the field is probably virtual reality. Because when we go on the field, we are able to really recognize features, to recognize the geometry of geological features, to have a 360 view of what is around, so to understand the context, and then from this to infer which could be the most interesting samples, the relationship between different samples, and so on. Next slide. I do not see the next slide. I don't know if you see it.
Yes, we do.
Okay. Okay. Yes, and now I see it. So because of that, PANGAEA is bringing the astronauts in different field environment, real field environment, real analogs. We go to Ries crater in Germany to study impact cratering, for example. With beautiful impact in Europe, the most well-preserved impact in Europe. We go to the Dolomites to discuss about geology in general, but also about sedimentary geology, which is related mainly to Mars, and also to actual robotic missions to Mars. And then we have the biggest session, which is in Lanzarote, where we bring the astronaut to see and experience volcanic environment, which are analogs to the lunar maria and to, of course, Martian volcanic regions. Another session which has not been yet delivered, but we have been working on this also with the University of Padova, with Matteo Massirone and Riccardo Pottobon, is about intrusive in Lofoten Island, and specifically about lunar highlands. So it's one of the few places in the world where we have very beautiful anorthosites, and we can really experience also this other part of the moon. All this, of course, means that we have, of course, lectures. We have lectures about geology, but then the most of the time is spent on the field. So with direct experience on the field to learn. And in Lanzarote, especially, we will see later, we do real traverses, and we will discuss. You can go ahead, Loredana. Okay, so there are. We started, as I said, in 2016, and of course, at the beginning, our focus was mostly to create training with very strong content, where we had to understand what has to be the main focus practically for the astronauts if they will go to the moon or to Mars. And so it was a big effort to develop the training and we had different editions in 2016, 2017, 2018. But in the last 2 years, we started also thinking how to apply virtual reality or augmented reality in the training itself. And there are two main applications of virtual reality for this kind of trainings. One is the support for traverse planning. So this is a realistic application that now we do here on Earth analog, but for sure it will be applied in the future in a real mission. So the possibility to use VR for a cooperative analysis of environments that will be the target of the exploration and the traverses of the astronauts. So this approach allows to have a preview of the environment, so to have a preview which is not just a satellite image or a spectral image, but it's a combination of all this information in a three-dimensional environment where also we have the sense of space and distances, which is extremely important because it projects not only the astronaut that will have to go there, but also the scientist to understand the environment and to really create a plan which will be targeting the most important features or samples and so on. So it allows this cooperative discussion and to recognize features that sometimes are not possible to be detected or understood just by classical survey with satellite images and so on. Then the other application is experiencing alien landscapes. So the astronauts have been on the International Space Station. They have been on the terrestrial analogs during PANGAEA, but actually nobody has ever experienced it aside of the Apollo astronauts, of course, which are quite old now and few has remained. But the new astronauts have never experienced really an alien real landscape. And so virtual reality allow us, if we have enough information from robotic missions, to really enter these environments from the moon or from Mars, to be able to have a look to geological features at multiple scales, and we will see later, to evaluate operational constraints, and to perform virtual traverses for understanding the geological environment, what we will need to do when the astronauts will be on the moon. Next. Okay, so this is the first application we are now working on for the next edition of PANGAEA. As I said, in Lanzarote, we do different traverses. Traverses are really a key part of the training because it's the moment when the astronauts really start not only to go on the field with the instructors to look to geological features and to learn about geology, but it's a moment when they really have to explore an area, a region, a geological region. They have to explore by themselves, of course, supported by the scientists in a science backroom. But this is a real exploration that brings to them the real learning that join together operational and field and geological information and issues. And so it's really, really an important experience. So they have to learn to explore autonomously. They are supported by the science team. And how it works, this process, it works it starts through a briefing with scientists. The scientist has some hypothesis on an area. So for example, you see this volcanic cone on the left. They have a geological hypothesis, and the astronauts will have to check this hypothesis, these scientific questions that need to be answered. So there is a discussion between the scientists and the astronauts, and also the discussion involves where we would like the astronauts to go, what could be interesting to sample, and what could be the constraints in terms of time and sites for sampling. And this briefing is really important because it's the first step that really will allow to have high performance and to obtain the scientific results that we are looking for. So usually this briefing was done just looking to satellite images and to spectral images, sometimes DTMs. As I said before, satellite images didn't allow to really understand the topography. So also to understand the problems that an astronaut would have to reach specific areas. DTMs can help in this, of course, but what we want to start now in 2018 will be, this briefing will be done in VR. Next. So specifically in this area of Lanzarote, which is called Tinguaton, we have realized, actually, mainly the Jacobs University has realized a very high detail DTM with drone photogrammetry. And this allows to transfer this DTM with the texture and the images in high resolution to a virtual environment, and to basically fly over this landscape and to bring the astronauts and the scientists together in order to be able to really look at the same feature at the same times before the astronauts will go on the field. We decide key points before, just to avoid confusion and to try to go fast in this briefing. And the instructor himself is together with the astronauts in the virtual environment. This is very important. Just a lesson that we have already learned preparing this kind of virtual environment is that we need to have tools which are useful, for example, to indicate with sort of laser pointers to indicate specific features that everybody has to look from different perspective, of course, because everybody is sitting sometimes in different points, different location of the virtual environment. In this case, we try to get everybody on a kind of a platform, a flying platform that allow us to really see all together and to discuss about the geological features. You can go ahead, Loredana. Okay, so now I want to just have, as you can see, this is a snapshot of the DTM, which is you see. Sorry, I hear some noise. Maybe there's someone with the microphone that put it on mute. Okay. You see already from these photographs that the resolution is very high, and that you can see really even small rocks, small objects that can be part of the discussion and to understand the texture of the terrain. So Loredana, if you leave me the screen, I will try to share mine. Okay. This is the model. You can see my screen, I think. So this is the model that can be seen in Sketchfab from Jacobs University of Tinguaton, and it's a DTM of the area of the traverse. Here you can see, of course, this is not the highest detail, but the detail I think is even up to a few centimeters in some area. So this is the field. As you can see, it's a pyroclastic environment, and the astronauts can really enter this environment. And flying over this environment or just landing on this environment, they can slowly perform all the traverse in a virtual reality point of view. And this, for example, if we go and look to this, to this caldera, we can have a completely different view instead of being looking to satellite images, because we can really look at the walls and we can see different layers. For example, we can already see different kind of colors, different geometries or boulders that will be potentially target of the astronaut. And when the astronaut will be on the edge of this caldera, we'll have exactly the same view as in the VR environment. So they will be much more efficient also in going and really targeting the samples or the units, the geological units that has been discussed together with the scientists. So this is for sure a very powerful tool. And while we have this on a terrestrial analog, of course, this could be done also on the moon, for example, because now with the Lunar Reconnaissance Orbiter, we have very high resolution images that we can apply on DTMs in high resolution created through photogrammetry, and we can create all what we need to pre-plan the traverses with virtual reality. Okay, Loredana, you can go back on the slides. So this will be the final traverse in Lanzarote in this year training, and we are planning to perform this kind of approach also to other traverses in the future. Okay, and now we go to this other topic. Okay, perfect, thank you. Which is experiencing alien landscapes, and I think this will be also showed in the following lessons this afternoon by the Plan Map team, the French, Nicolas Mangold and the French team, because this is also something which is really nice for the astronauts to understand. Because during PANGAEA we talk about different geological environments on the Moon, on Mars, and we have also a lot of exercises that bring the astronauts to really learn about a specific outcrop, because practically it's exactly what they will have to do, is to recognize different geological features, to recognize their relationship, and then to identify which could be the most important samples. So if this process is done quite quickly and efficiently, then the traverse is successful. Otherwise, they need too much support from the science backroom, and this could be even not the case on Mars, where we have time delay. So this is just an example. It's a beautiful exercise that is done by Nicolas Mangold, one of the instructors about sedimentary geology during PANGAEA, and shows different outcrops which has been documented by Curiosity rover, and bring the astronauts through all this process. This can be done also in virtual reality. You can go ahead. If from the information that we have from Curiosity, we can recreate this environment, for example, through photogrammetry in virtual reality. I don't know, I can, okay, perfect. Then we can insert a lot of additional information. And this information could be related to different scales. Now you can go back. Okay. I think you can go back to the previous one. I see the lava tubes. Okay, thank you. You can add different scales, and also information about analytical tools. And this information can help really to understand better also what the astronaut will be able to do and achieve in terms of additional information, not only just look into the outcomes, but using, for example, analytical tools and so on. So this is not really an exercise that is focused on operations, but it is more focused on how we will be able to learn the future. So it's looking really to the future of application of VR. And also the objective here is not really how we can perform a traverse, but it's really what we could see on another planet in terms of geology, and how much this is similar to what we have seen on the field during PANGAEA. When we go to look to sedimentary environment, we go to the Bletchley Canyon. It's a really nice place with a lot of analogies where you can see several of these formations. Go ahead. That, of course, would be nice to have this kind of virtual environment for several situations and missions to the Moon or to Mars, because they really allows to have a different point of view, and it's much quickly also for the astronaut to learn and to point to specific feature instead of just looking to images, or instead of even looking to analogs on Earth, because sometimes we have some differences because maybe the size, maybe the relationship, maybe other features that looks the same but are not exactly the same on other planets because of different planetary conditions, and we could see them directly in VR. This is another example. During PANGAEA, we do also a campaign which is called PANGAEA X. It's a testing campaign, so it's not really related to training, but to testing new application and for geology. for field geology involving different institutions, even companies. And in 2017, we have done a PANGAEA X in Lanzarote, involving the different universities and also Leica to perform 3D models of lava tube environment. And this was a very nice experiment because we have been able to, together with Leica and BiGeA, to perform the scan of one of the biggest lava tubes on Earth, Corona lava tube, and they obtained a 3D model of about 6.5 kilometers with a resolution of about 3 centimeters per pixel. So this allows really to explore, let's say, complex and extreme environments, and to model how these environments could be on other planets. We know that we have lava tubes on the moon, on Mars, and this model has been used also for modeling actually the dimension of lava tubes on the moon and on Mars. And we have recently published a review about this and showing that lava tubes could be really huge on the moon, up to 2 orders of magnitude bigger than on Earth. Of course, this can be used also for outreach activities, which is nice because we can show places that are like on the moon will be not visible for the public in this way. So the next slide, I think there is a short video, Loredana. We can see the 3D model. This is a mesh, so it's not with the real texture, but of course there are also all the model has also colored pixels. This is the tube of Corona, and so of course this kind of applications, creating a model like this is something that a few years ago was very complex, but now, as you have seen also in the photo before, there are technologies that allows you to go with a backpack, with a mobile laser scanner, and to get almost in real time information that can be shared with anybody, and can be used by scientists remotely to really understand the environment and the geological features. Okay, next. So I just draw the conclusion, then I will leave to Loredana to add something. Virtual reality or augmented reality, it's surely very, very important for training, and it has been used and will be used a lot in space exploration in all different phases. So from design to testing to training to operation, and then of course for outreach. However, there are some very important things to keep in mind. You need to have a really high fidelity with the real with reality, because especially when you do training, this doesn't apply when you do outreach, of course, but when you do training or testing, deviation from reality can then afterwards create errors. And this is extremely important. It's the most important things to avoid. So it's not an easy task to use VR, because we need to have high fidelity environments. If we train in an environment which shows exactly how the space station was 10 years ago, this is not good, because the astronaut, when will be on the space station, will find a different situation, and potentially could not be beneficial for him, or even could create problems. And another very important point is the fact that we need to currently add the new information knowledge. This is the case, and will be the case, for example, to the moon, when we will have an astronaut going to a traverse. He will get information, and we will get new information, higher detail than what we can achieve from satellite platforms. And we will need to be able to add all this information very quickly to allow to integrate this information in the virtual environment for further advancement of the traverse and of the research. And also we need collaboration tools, because VR allows you to put together different roles. Actually, you can put is able to put together in the same environment, for example, the astronaut with the scientist, and these entities has to collaborate, and we need to be effective in this collaboration. And the key, so for virtual reality, is that virtual reality has to respond to the needs of space exploration, and every virtual reality application has to be focused on real goals and very clear goals. So I finished. I don't know, Loredana, if you want to add anything.
Yeah, I just want to add, imagine now that we could actually have virtual reality to go through this meeting. You could see each other and you can really interact with each other, passing tools and building planetary maps together. So that's what you want to achieve. You want to be able to suddenly change the environment, say, okay, we're moving to Mars now, and currently you are on an updated Mars environment. You're changing the granularity at which you're seeing it, you're changing your perspective, and you see whom you are with. This is what you really want to achieve. If you can do that, that's fantastic. And imagine how much better your experience this week would have been. With that, I would like to thank you for listening to us. And I don't know if you would want to have questions or otherwise I'll pass back the control and I stop sharing.
If you have a question, you can use also the chat.
So either we were boring like hell and you actually didn't want to, or we're scaring you. Don't be scared. We can't beat. We are not in virtual reality yet.
I do have, it's not really a question, it's more a comment on VR. So first, thanks for both of your talks. It was really interesting. I really know nothing about VR, and the 2 times I've tested it, it gave me a headache. But I saw a documentary about archaeology mixing with VR, and I don't recall exactly what it was about, but it needed a medical statement about an archaeology finding, and with the VR they associated with not exactly an X-ray, but a method of seeing through the objects. And they ask a medical statement from a doctor, and he was able to state what condition the body was in, etc. So it was quite interesting. And like you said, it would be a completely different experience to have had a virtual meeting with the VR associated. So yeah, it was just a comment, not really a question.
Yeah,
I saw the documentary. I saw the same documentary.
Yeah, you are true. And also this has a lot of application for geology, because what we show now was only DTM, so surface geology. But PlanMap has been doing great work for creating 3D models of the subsurface. And of course, having the possibility to experience these 3D models in VR will allow much better interpretation, I think. And also imagine that you are going with an astronaut is going on the surface of the moon with the GPR, a ground penetrating radar. And this information is going directly to the ground and elaborated in real time. And then you could get a virtual environment where you can really see below your feet. So you know that maybe you have different units, just few centimeters in the regolith just below your feet, and maybe just drilling or using a core sampler, you can get them. So this has a lot of potential.
Yes, I agree.
I see. Well, one question. Unfortunately, I mean, the question from Hamilton, wait for people to do the PANGAEA training. Well, the PANGAEA training is for astronauts and mission controllers, but we actually, I mean, the training is done by planetary geologists like Matteo Massironi, Harald Hiesinger, Nicholas Mangold. So those are the instructors. I think you can't participate unless you're an astronaut, but definitely you can participate to training and field trips from those folks, because there are, I mean, you can't have a virtual one of them. You need to have the real ones. The other, there was is it possible to collaborate in the project proposing new potential analog areas? I mean, talk to Matteo, Harry. Those are the people that are working with us. We currently are not looking for different areas, but for sure, as we're going to enter into the new area of planetary exploration, there will be a need for more field trips in collaboration with other space agencies, and definitely having new areas being represented. That is going to be interesting, of course.